Thanks a lot, Peter. Hi, everybody. It's great to be here. Great to see everyone, some new faces, some familiar faces. And as others have said, this is a really, really pretty campus, which I find quite lovely. I'm going to start talking today about some of the ideas that we've had and things we've been playing with on how to improve our data. We start this, maybe. Down is the new up. Okay, down to go forward. Where do we use two-dimensional GC mass spec? And I've been using this for a while, a technique for a while, and my lab uses it for a variety of things. And if we think about where people use two-dimensional GCMS, where we have complicated samples, so petroleum, environmental samples, all kinds of omics, foods, flavors, and things like that. And why are we using this technique? Well, generally we have a very complicated sample and we're trying to answer questions something like this, are there any compounds in my sample that are maybe harmful or that are regulated and I need to worry about, indicative of some kind of exposure or otherwise interesting or important? And when we're faced with these really, really complex samples and that, two-dimensional GC, possibly with a high-res mass spec or with just a normal mass spec, is a perfect tool for looking at this. And if we look at two-dimensional GC, the reasons it's so good is we have this expanded separation space. That's at the very first thing. And what this gives us is a whole pile of tools. First of all, it gives us nice pure peaks to introduce to our mass spectrum, so we get cleaner mass spectra, higher quality mass spectra than we would from a 1D technique. And these higher quality spectra can help us with better compound IDs. If you happen to have a high-res mass spec, even better, because then you can start playing all the tricks you can play with high-res mass spec, and those are a lot of fun too. We have better sensitivity, that's not up here, for this because it's not as important for what I'm talking about today, but we have interpretable retention patterns, which are also really useful. We, with our knowledge, our experience, our brains, can sit down and just looking at where peaks are relative to each other, say a lot about the sample. So Haley today, I'm sure, could sit down, look at a diesel chromatogram and tell you every single peak in there and read it kind of like you or I would read the newspaper if we picked up one of those, anachronistic things. And what I'm talking about a lot today is an old story, right? We have, and this has been ever since I started doing this longer ago than I care to admit, we have hundreds or thousands of peaks per sample. We have lots and lots of samples. In some of my projects in my lab, we might have 700, 800, 2,000 samples. We don't have a lot of standards, and even if we did, running all those numbers of standards would take up an inordinate amount of time. We have really high quality spectra, and we have these powerful retention patterns. Things that we need, well, one of the things we really need is a coherent and aligned peak table, or featured list of what the things we have in this. And we want to also have really nice, consistent peak identification. So what I mean by this is, if in one sample compound X shows up, it is labeled as compound X. Nothing else is labeled as compound X. If you have a second sample that is run, compound X shows up in that sample, it's also labeled as compound X. If you have a sample where there is no compound X, no other peak is mistakenly labeled as compound X in your peak table. This is what we're trying to avoid. We want to get a really nice peak table. And the big question for a lot of this is, how do we meet these needs quickly, reliably, without losing our minds or, relying on tormenting our students who spend hours curating peak tables to make sure they get good results? It works, but it's really, really tedious. Is there a way we can do better? So the data that I'm going to be showing today comes from a pair of studies. The first bit of data, or some of the data I'm showing, is coming from this project we've just started with a bunch of colleagues looking at the transport and environmental fate of potential spilled oils in the Arctic. So looking at all kinds of things that could go wrong with the increased shipping in the Arctic as the Arctic opens up because the climate is warming and changing. And also looking at some of the new marine fuel oils that are out there that are being used and how they will behave in the environment. All that stuff is really at the beginning, so most of what I'm talking about today here is just I'm pulling some data from some preliminary analyses of a variety of fuels that we looked at. We also have data on a field pea project that one of my students is about to write up, that she's been working on with some colleagues in biosci, looking at how water and nitrogen and et cetera, impact peas and the growth of peas and the VOCs that are produced by pea plants under these different conditions. Just to give a quick look at what a chromatogram looks like, I'm not going to show you chromatograms of fuels because we know what those look like, but this is sort of a typical chromatogram for peas under a couple of different conditions, and these are pea volatiles collected by active sampling of the air around the pea plant onto a thermal desorption tube, and then the tube is thermally desorbed, and we go off and do all of our data analysis afterwards. And this stuff was all collected on our 2D GC high-res that we have from LICO. So if we look at the basic workflow, and this is the workflow a lot of people use when they go to try and work up their data, they run their samples. For every sample, they do their peak finding, then they do some library searching, and they get a peak table, and then they try to put these things together. And you do this for a handful of samples, and much like poor Cosmo here, as I was leaving for the day, and he was very sad and saying, "But Dad, why aren't you taking me with you?" We have other problems too as we look at this, and the students are like, but what do we do with peaks that are close to the signal-to-noise cutoff? Or peaks that have poor library matches? Or for trying to reconcile all of these different peaks across all these different peak tables, what can we do? And there are a lot of tools that people are developing, and a lot of tools people are developing that are, some are coming into commercial software. There's a ton of lab-based custom solutions that people have. But one of the things I want to work with my students, because most of them don't want to code, sadly, is working with a workflow that uses tools that we already have in the software. We don't have to write a bunch of special code on our own. If we want to, we can, great. But if you don't want to, you can just use the tools that are in the software. So the workflow we're generally working with, and I'm pushing them to use more and more, is this retention index and IGS, so the peak identification and grading system. I think that's what it stands for, that LICO has built in for the high-res data. And the workflow here is kind of similar. We run our samples, we do our peak finding, but in here we also have a run of N-alkanes that let us calibrate our retention index method. And now we can calculate experimental retention indices of all of our peaks. As we do our library search, you can filter your library search with the retention index. If you have the IGS scoring, you can then apply this kind of scoring and only retain the peaks with a score greater than 3. John Hayes gave a talk on this a number of years ago. It's a really, really cool toy that I think is really underutilized for getting a peak table. Now, we're using this stuff built into Chromatoph, but much of this could be implemented very easily in other commercial software or pretty easily outside of commercial software, as long as you get a decent peak table and spectrum that you can dump out from the software. So just looking at our P data a little bit, here is a peak table that if you just do the normal filtering, normal analysis, and you get your peak table for one particular sample. This sample here has a whole pile of compounds that don't have a good library match. They're the ones that show up as peak and some random number. We have no retention index information here and no other scoring. We have 800 peaks roughly. If I now add in retention index filtering and add in the peak grading system here and only keep peaks with a score of 3 or better, I now have, for this one P sample, 146 peaks that I'm reasonably confident in the identification. And this is done automatically with the processing. It's trivial to do this. And I've got, compounds, I've got decent retention indices. They match reasonably well with the library. And the nice thing is I get this concerns column that starts telling me what I need to worry about. Here, I don't have a molecular ion. I can look at the compound. I don't care. I'm not going to have a molecular ion for that peak. So what? That's a pretty good match. It kind of helps. This also shows up with our alkyl benzenes. Well, it shows up all over the place in complex mixtures, but I'm just going to take my alkyl benzenes and pull them out of our petroleum sample for a bit. So this is one of my petroleum samples. I think it was some medium distillate that we have. And this is the XIC for a series of C3, 4, and 5 alkyl benzenes. So I've got my C4 alkyl benzenes over here. Sorry, C3s are over here. C4s are coming in here. C5s are over on this end. And I'm just looking at these 3 compounds here for a second. Peaks A, B, and C. Here are the different samples that we have. So I've looked at them in 5 different of the different fuels that we were looking at. Here's the name that was given to them, and you can see that in every case, they're guessing kind of similar things, but sometimes they'll have disagreements with where exactly are the 3 methyl groups, and all of these have really basically a perfect score. The retention index is a good enough match. The spectral quality is great. All the right ions are there, et cetera, et cetera. So the problem is now when I get this peak table, or my student gets this peak table, and in some, they're calling it this peak here 1,2,3 trimethyl, same peak, sometimes 1,2,4, maybe 1,2,5, 1,3,5, who knows. They need to get all these things lined up in their ultimate peak table and the same name for everything so that they can make sense. So here's where we ask, can we do better? This IGS strategy, it's working well. It lets us keep our good peaks. We get high quality spectra, good library matches. The retention index usually makes sense. It does a pretty good job of catching known knowns, what they are, you're looking for them, you expect to find them, and catching our known unknowns. Those are peaks we're not looking for, but we know what they are when we find them. It struggles a little bit with some of the isomers, and it ignores the truly unknown compounds where we have no idea. But one of the things we really want to try and do, especially if you're looking at exposures, environmental data, what about the unknown knowns? This 4th category of peak that people kind of ignore. And these unknown knowns are compounds which we have learned to expect to find. We always see them in our samples. We don't know what they are, but they're always there. So they're unknowns, but we know that they're there, so they're expected. Well, to deal with this is where we've started building our custom library. In this case, it's custom high-res library, but you can do the same thing with low-res data. What do we add to the library? Well, spectra of standards, known compounds. We can also add unknown knowns, and we can also add things like these. So let's say I know that that's non-anal because I have the standard, I ran it, I've got a good spectrum. I have these interpretable retention patterns. So everyone in the room should be able to very, very quickly identify every one of those peaks that's also in the sample that has an arrow pointing at it, and also the little guy right there that I forgot to put an arrow on. But those are all a series of linear aldehydes. And you look at the spectrum like, yeah, that's a linear aldehyde. I know exactly which one it is. Let's add it to the library too. we're building this library, we have to have some rules. So if we're going to be building a library, we want to add a spectrum or add a peak, it has to be a good peak. By that we mean a pretty good signal to noise. We generally use 100 or 200 as a cutoff. It has to be chromatographically pure, so it's a good, clean spectrum of that compound. We also want it to show up in multiple technical replicates or multiple samples from our study because we want to make sure we're not adding some spurious bit of garbage that just showed up. We also must have a retention index value for the RI collected on our system, and then we'll give it a unique ID. We might give it its name, or if we don't know what it is, we can just give it a code, like your initials and a number. We don't even need to know exactly what the peak is, or even have a partial idea of its identity to put it in our library. If it becomes an important peak 5 years from now, we can go back and rename it and give it a name. And then our library is, improved that way. What do we do with these peaks that are, either uncertain or that don't have a name, though, and don't have a library match? At least, so are these uncertain peaks. So this right here is an example of a C3 alkyl benzene. We don't know which one, because only one of them showed up in this particular sample. And they all look pretty much the same. So what we did was we just picked the most reasonable hit and called it, peak number 10, it's a C3 alkyl benzene. And that's what its name is now in there. At least in the chromatoph environment, if it doesn't have a name and a hit assigned to it, you can't add it to the library. So just pick a hit, assign a hit, then add the spectrum to your library and edit the details and change its name and all that kind of stuff. So now what happens if we start looking at our peak tables, and this again is coming from the P's. Here are the different samples I have. If I just do a simple workflow with the NIST library, the number of peaks that I get, here's the number of peaks that I get if I include retention index filtering, number of peaks with an IGS of 4 or 3, and then this is sort of the overall retention index error calculated using this formula over here for all of the peaks that have a retention index, all of the peaks that have are of these 75, and all of the peaks here of these 71 for IGS3. So we've got an error of, plus or minus 20 retention index units. If I now use my custom library and search that, well, adding in my custom library, now I have way more compounds with a retention index, or not way more, but appreciably more compounds with a retention index, more IGS 3 and 4 hits. 41 of these peaks were in my library for this particular sample. And then here are the numbers there. And then these are the retention index errors that we see. And when I start using my own library with retention indices collected on my own system, these errors start going down. But that's not where it gets really cool. Where it starts getting really cool is if you do this and then you dive a little bit deeper into your peak tables, my library error for looking at the retention index is generally incredibly small, except in places like this. And so this is the square of the retention index error, just to make sure I always have a positive number. And I have, for example here, this compound here, it's actually identified twice, so they're probably isomers. And it's very easy to say, oh, well, this is the one I know, this is something else, I need to reassign this peak and give it a new name and clean that up. Likewise here, this is another alpha pinene. It's not actually alpha pinene, it could be beta pinene or another terpene. Fix that. And another one over here. This is undoubtedly another branched C21 hydrocarbon, just not the one I had already found. So finding your problem peaks is now trivial, right? Like it takes 20 seconds to look through a huge long peak list and say, here are the 10 compounds I need to fix. or figure out. So now, what happens to this retention index library, my errors here, my retention index error, if I fix those handful of problem peaks that I have in the peak table? And if I do that, we see that these errors get incredibly small. Enough to make this guy really, really, really excited. So that's really, really useful. Also really useful when you build your own library and start using it and searching it first. Here are 3 compounds that I just picked out of the P data. All these peaks with my custom library always got identified as the exact same compound. With just using the NIST library and not my library, this peak here was given all these different names. How are you going to line up all those random peak numbers? It's very, very difficult trying to sort that out. This one here, again, not found, few different numbers here, not found, few different numbers. Here it was found or maybe found as some other C3 alkyl benzene, so I don't know if it's the right one or not. And again here, found right ID, random number, right ID, random number, right ID. So just a couple concluding thoughts as we wrap things up here. You should really build your own MS library that includes retention index data collected on your system and search that first. That will really help you get really, really precise retention indices and let you really tighten in that retention index window of what's an acceptable shift. Plus or minus 2 probably is what we're going to use for a lot of our stuff going forward. So now you're really zeroing in on what are these specific compounds, and your isomers should be really easy to sort out every time without you having to do a lot of manual reviewing of your data. Add your unknown knowns. If it's a peak that you always see, add it. Call it Bob. Who cares what you call it? Just give it some name and just say, oh yeah, I always see you. You're always going to be identified as the same thing. You got a garbage name. Someday if we figure out you're important, we'll identify you and give you a proper name. But for now, we'll just call you Bob or whatever you want to call the peak. Again, yes, collect your local retention index data. If you have it, apply the IGS filtering. If you're not using Chromatoph with a high res, you can still do a lot of similar stuff outside afterwards in your peak tables with pretty simple scripts. And what all this does is it lets you get better peak tables in less time. They make a lot more sense, make your downstream data analysis and chemometrics much easier because the same compound's identified properly in every sample. And another little bit of thing is also learn to write Excel macros and or write simple code. It's hugely, hugely helpful for making your way through all of these things and well worth your time. And with that, I'll just thank Lico, who's helped us out a lot with instrumentation and software, our major funders. So I'm part of the Metabolomics Innovation Center, and we're funded primarily through the Canada Foundation for Innovation, Genome Canada, and Genome Alberta, and a lot of this was also funded by NSERC and the University of Alberta. And Jared and Han right here are working on the oils, and Sherry right here, she's working on the P project and other plant volatiles.